so this is saved forever. I'm going to open your minds to another type of graphing system. Okay, throughout our entire mathematical lives, we've been stuck in the XY plane. We have an x-axis, we have a y-axis, and we've been plotting points in this two-dimensional axis based off of x distances and y distances. This seems obvious to you, however, it is not so obvious when mathematicians first kind of started plotting things in 2 dimensions. There's lots of different ways you can put a point right here. But we've been used to saying that this point is at the location 2, 3. -4, 2. An x distance of -4 units, a y distance of 2 units. And then we have functions. Y equals 2x minus 1. And we were taught when we were first dealing with this function, pick some x's like 0, -1, 1. Plug it in and get the y coordinate that goes with it. If I plugged in 0, I got the y coordinate of -1. And then plot that point, 0, -1. And then I plug in 1, and I get 2 minus 1 is 1. Plot that point. Let's choose -1. -2 minus 1 is -3. Plot that point. And then you were told, oh, take those dots, 2, 3 is also a point, and connect them and extend them. But why are we connecting and extending some of these points? It's like a lot of people forget. Why are we doing this? Why do we connect and extend them? Why? Why did I connect those points when I graphed y equals 2x minus 1? Good, Miss Lowy. Miss Robertson, put your phone away. Because there are multiple solutions besides the ones at the whole numbers, right? Are there points, x values in between 0 and 1? Sure. Do they have y coordinates that will correspond and satisfy the function? Yes. So why do we connect and extend? It's because what we should be doing is plotting all of these solutions. And when we keep plotting solutions and plotting solutions, what happens to all those solutions? They end up just like blurring together and making a line, okay? That's like a side note thing. And we are dealing with infinities a lot in this class, and we can think about being infinitely close, but having a point, right? Cool. Well, shift away from that old way of thinking to a new way of thinking. Polar coordinates. Polar coordinates are r's and thetas, not x's and y's. Now, we are going to plot 2, 3 in a second, but how we are going to plot that is very different than how we plotted x's and y's. So remove your minds from x's and y's. We are first going to start with this theta. Theta is the math way of saying an angle. So this is going to be an angle on which my point is placed. And then we will go to the r second. And r, think of it as a radius, is a distance away from the origin. Okay? Now, let's plot 2, 3. Well, I need to think about angles first on a coordinate plane. Well, no longer am I calling this an x-axis or a y-axis. Instead, I'm going to say, well, this is where theta equals 0. This is my 0 angle. This is where theta is equal to pi over 2. This is where theta equals pi. This is where theta equals 3 pi over 2. Okay? I'm going to use a straight line to denote an angle. I recommend that you guys, when dealing with polar coordinates, use a pencil, a finger, your hand to understand a changing angle. So here's me changing my angles, right? So I'm going to go first to an angle of 3. 3 is very close to one of those numbers that I placed up. Which number is it close to, Mr. Stockton Peter? 3 is very close to one of these angles that I placed down there. Pi over 2, pi, 3 pi over 2. Which one is it close to? The actual number 3. Right, because pi is 3.1415926.535. That's really close to 3. Okay, so I am going to first go to the angle of 3. Now I need to go a radius of 2 units, a distance of 2 units. How do I do that? Well, what's going to help me is, my friends, the circles. We'll call this a unit circle. That means every single point is 1 unit away from the origin. Does that make sense? Well, then this can be a circle with a radius of 2. And this is a circle with radius 3. So I've gone to the angle 3, and now I'll go a distance of 2. Here is 2, 3 on my polar coordinate system. Completely different location than 2, 3 on the Cartesian coordinate system. Correct? Now, typically, we will not use angles at 3, right? Because we don't know exactly where 3 is located. We have no reference. So we're going to use the angles that we are familiar with from pre-calculus, like pi over 2s, pi over 6s, pi over 3s, all of those. I'm going to plot a couple, then you guys are going to plot a couple, and we will make sure we all have the same answers. So I will do 1 pi over 2. Again, it is r than theta. I will go from 0 to a theta of pi over 2, a length of 1 unit. So there's pi over 2. Here's 1 pi over 2. 5 pi over 6, 3. Really the same thing. I will go to a theta of 5 pi over 6. 5 pi over 6 is right here. Let's say it's more like here. All the way out 3 units, closer to here. And this is the point on the polar coordinate system, 3, 5 pi over 6. Fairly close to 2, 3. Now here's a new one. -2 pi over 3. So again, first I go to pi over 3. How do I do a -r? Ideas? What do you think, Miss Cood? Yeah. What did you do there?
Instead of like going, I guess, kind of like following your line, you just go off.
Right, we will just go opposite of where my angle is going. So instead of going out 2, I'm going to go the opposite way 2. Incredible how you already have that down on your piece of paper. That's good. Okay, so I got that. You guys do these 4. I'm going to throw up another one. Go. That's a -1 pi. Yes, correct. Where's that go? Doing it in your head, Miss Noakes?
Yes.
Okay. I'm going to call on you then. Very happy to see you BC students who took the BC test. Having these already in your notes shows me that you actually watched this video before you took the exam. Ms. Ali, did you already watch this video before you took this exam? Yes. Did you do well on the polar question on the BC exam?
Maybe.
We'll find out. We're going to do parts of it next class. Yep. Please lean on those who've already learned this lesson. So the Stocktons, Miss Ali, who else? Miss Cood, already learned this lesson. Did you learn this lesson, Miss Cha? Miss Cha already learned the lesson. All right, collaborate. Make sure you have the same answers as your neighbors. Like -1, -pi. What the hell is that? Oh. Good. This is review. Yes, this is review.
Yeah, backwards. So yeah.
All right, -1, -pi. Mr. Johnson, where is it?
To the right.
To the right of the center. Okay, good. So here's -pi, right? We go this way, and then how many units are we going? 1 to the right. So right there is -1, -pi. 0, 7 pi over 6. Where is that located, Miss Lowy? Yeah, at the origin. It's crazy. We're at the angle 7 pi over 6 over here, but then the distance is just 0 units away. So we're at the origin at an angle of 7 pi over 6. Let's see. What else? 1, 3 pi over 2. That ends up being down here. That's easy. -2, 7 pi over 6. We're already at 7 pi over 6. I'm going to go to -2. Okay, and I'm actually going to put this guy in red, because there's one huge difference between the Cartesian coordinate system and the polar coordinate system. Okay? Now, obviously, r's and theta is different than x's and y's. That's a huge difference, yes. But there's something else that is just hugely different about this coordinate system compared to the Cartesian coordinate system. Discuss with your neighbors what you think the difference that I'm looking for might be.
What is the Cartesian code?
X's and Y's, Mr. Stockton. What do you think, Sanj? Very nice.
Yeah, fun.
Okay. Well, very nice, Mr. Stockton. Okay. So, a non-BC student, a non-BC test taker, ideas. So, Mr. Johnson, you didn't take it, right? Mr. Kobayashi, you didn't take it. What were your ideas?
How like negative numbers, it like doesn't change. I'm trying.
No, you're good.
Like how you can have a negative number and be in like the first quadrant.
Yep, definitely. That's definitely a big thing. And what does that enable us to do? Not sure?
Not sure.
Mr. John, Miss Lowy, what do you think?
Is that like you can have numerous numbers of locations?
Yes, exactly. It's exactly what I'm looking at. At the Cartesian coordinate system, each point has one distinct xy. That has only one xy. You cannot list it any other way. But in the polar coordinate system, we can list -2, 7 pi over 6, multiple ways. So give me another way to list -2, 7 pi over 6, Miss Noakes. I told you I'd call it on you. Exactly. Excellent, excellent, excellent. We can go to +2 with an angle of pi over 6. Give me another way, Miss Waugh. So 19 pi over 6 is 7 pi over 6 plus another 12 pi over 6. You went around the circle. I like it. Usually students do not go beyond 0 and 2 pi, but you are thinking out of the box. Excellent.
That's the only answer.
No, there are other answers. So, Mr. Stockton Chris, give me another one. Come on, you can give me another one. I'm not sure if negative 31, how many is that? Is that 5 pi? So if you go to negative 30, 2, 3, 4, that's 5 pi, and then you go one more, this is negative 31 pi over 6. So you need to go to negative what? If this is negative 31 pi over 6. I need to go back to, so you go to negative 29 pi over 6, that works. But let's just stop talking about the negatives and let's stop going with negative radius. All I have to do is just go halfway around the circle and take an opposite, or if I go a multiple of 2 pi, if I go all the way around the circle, I can go back here with a positive. So if I have pi over 6, go around the circle again, we're at 2 pi, which is 12 pi over 6, add 1, 13 pi over 6, 2. Okay? So that's another one that I was actually looking for, that one. But that's okay. So big difference is that there are an infinite amount of ways to list any point. List. What am I doing? Okay. Now, this makes for interesting graphs. We are going to graph 4 cosine 2 theta. Now, we are used to y equals x's. In polar world, it's r equals thetas. Now, it's really interesting. You know, x came first and then y, but here we have r coming first and theta. Any guesses why it's r theta when we do theta first? I wondered this myself. Good, you guys really paid attention to the video. So we do r's and theta in math because they like to list things in alphabetical order. So even though theta is our independent variable, it comes second because t comes after r. There you go. All right, so here we go. Now, it's the same thing as how we graph, y equals 2x minus 1. We pick some independent variables, we plug it in, we get some dependent variables, right? So we picked 0, 1, negative 1, 2, negative 2, easy numbers to work with. But we're not going to pick thetas 0, 1, 2, 3, negative 1, negative 2. And why wouldn't I pick those thetas? Not on the unit circle, not easy to find. I do not know what the cosine of 2 is. I do not know what the cosine of 4 is. So my independent variables that I will be picking for theta are like the ones I know. 0, pi over 6, pi over 4, pi over 3, pi over 2. We'll start with those. So these are my inputs. I will then plug it in. Mr. Stockton, put your phone away. I know you already know this stuff, but it doesn't matter. You can just help others. We plug these in to find r, so I have 4 cosine 2 times 0 is just 0, cosine of 0 is 1, and then I list my r comma theta in the opposite order. Cosine of 0 is 1 times 4 is 4, comma 0. Okay, let's find the other points. I'm going to do this quickly. You guys are going to do a couple more in a second. This is 4 cosine 2 times pi over 6 is pi over 3. The cosine of pi over 3 is a half times 4 is 2. So this is 2 comma. Don't use the changed angle. Use the original angle, pi over 6. Pi over 4. 4 cosine pi over 4 times 2 is pi over 2. Cosine of pi over 2 is 0. 0. Pi over 4. Don't use the changed angle. Use the original angle. Cosine of pi over 3, it's 2 pi over 3. Cosine of 2 pi over 3 is negative a half. We are in the second quadrant times 4. Negative 2, 2 pi over 3. Again, don't use the changed angle. Use the original angle. I even make that mistake myself. And then finally, pi over 2. 4 cosine pi. Cosine of pi is negative 1, so I have negative 4 and pi. So it looks like we have r's of 4, 2, and 0. Let's go ahead and give our plane a circle with radius 2 and a circle with radius 4. Don't you wish you had that capability on your piece of paper? And I would like you guys to plot those 1, 2, 3, 4, 5 points. Ready, set. Gosh! Can't believe it. I like repeatedly say it and I still do it. All right, I'd like you to plot those 5 points. Then I'd like you to connect them as you see fit. Let's see if we connect them in a nice way. Let's plot these points. Let me see them. Good. Now connect them as you see fit, Miss Theta. Maybe do it lightly or just have an idea of how you'd like to connect. Okay, good. All right. If you have a pen, maybe take it easy. Very nice, Miss Morton. That's what I like. Good job, Miss Lowy. I like what Mr. Stockton did. I like what you did there, Miss Robertson. Excellent. So, really quick. All right. Now, when you are using these angles, remember, you have an angle. So think angles. So start with your pencil or a line with your angle, okay? I like that. I will use this and move this and plot my distances. So I have 0, 4, 0. I have pi over 6, 2, right about here. I then have pi over 4, 0. Think, when we get to the origin, a lot of students make the mistake. They forget about the angle. But here we are at the origin. And then all of a sudden we got some negative radiuses. I go to pi over 3 and I get negative 2. And then I go to pi over 2 and I get negative 4. And Miss Robertson, how did you connect them? What did you do? Right, looks like we got some sort of parabola, right? So it's important that we are connecting them in order. If we did not connect them in order, it's like, I don't know. So understanding where things started and went is important, okay? So then Ms. Robertson said, well, I'm used to things trending off towards infinity, so I'm going to go this way, right? That makes sense, logical, we've done this before. But your turn. Let's pick some more angles and get some more points. So why don't you guys start plugging in 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Go. And find the radiuses and plot those points and see where the graph takes us. Mr. Kobayashi did the same thing. We assume we just trend towards infinity. No, it's okay. That's correct. I want to point that out because that's an assumption we like to make. Why don't we pop our eyes onto the screen when we have ours to check to make sure we are all correct. All right, check up on the board. Make sure we have the same answers. Oh, man. That's bold. Super bold. But he's the principal. He can do whatever he wants. He just took your pretzel. There's only 100 calories in there. Oh, my God. 90 now. All right. Okay, so watch what happens. I go to 2 pi over 3, and I don't keep going out. I come back in. 2 pi over 3, negative 2. 3 pi over 4, 0. 5 pi over 6, back to being positive. Pi, positive 4. Oh my goodness, get this out of my face. This out of my face. Continue to connect in order and watch what happens. Pretty neat. You think it's going to go off towards infinity on those directions? Nope. If we continue to go and continue to plug in points, we'd find at 7 pi over 6, radius is 2. A pi over 4, 0. We go to 4 pi over 3, negative 2. So all of a sudden we come back, and then we pop up here. 3 pi over 2, negative 4. We're now at what angle? What? No. Oh, I'm at 3 pi over 2 now, and I've got negative 4. Well, what's the next angle that I'm going to plug in? Come on, pre-calc graduates. What's the pi over 3 after 3 pi over 2? 5 pi over 3, thank you, Mr. Johnson. 5 pi over 3, negative 2. Another 3 pi over 4, this is 7 pi over 4. Another pi over 4 is 0. And then we have one more point, well, 2 more points. We have the 11 pi over 6. We get a positive 2. And then we're at 2 pi, and it ended up being the cosine of 4 pi, which is 1 times 4. And we get this graph. Well, what if I kept going? What if I went to 13 pi over 6? Where would I be? Out here? No, I would just end up going back over. And if I go to 15 pi over 4, is that right? Who knows? The next pi over 4, we'd go back here. And then the next pi over 3 would be here, then pi over 2. And all of a sudden, as we continue to graph thetas, we would continue to trace over in this manner. Pretty cool, right? Your calculator can do this. Oh my goodness. No way. Prove it, right? You know, it's really funny because we've been using a button our entire lives, and we've known a button. Oh, don't see this. Hold on really quick. Okay, good. We've been using a button our entire mathematical lives, and we know it as the X button, right? Where's the X button? Under mode, right? This button's X. Why has it got T's and a theta and an N when it's just X? Right? Oops. Well, it's because I pressed epsilon, huh? Well, it's because of your mode. Go to your mode right here. This line changes the type of kind of equation that we can plug into our calculator. And if we pop over to polar and press enter, go ahead and press that X button again. It's not X anymore. All right? And go ahead and press Y equals. What happens? It's not Y equals, it's R equals. And we have 4 cosine 2 theta. Go ahead and plug that in and graph it. There it is. Pretty nice. Okay. Now, go ahead and press trace. And explore trace a little bit. Get your cursor over your graph. Move it around. Left and right kind of changes. Right? Up and down doesn't really work, does it? Why can't I go left? That's weird. And then when I go right, what's going on? The angle is changing, and it's the angle that they are telling us. I get to a certain point, and all of a sudden I can't go any further. Very interesting. Well, there's a very good reason for this, because the graph will repeat itself forever and ever and ever. If we told our calculator to just graph this, it would just keep going unless we gave it a little bit of a constraint. The constraint being the angles that we would plug in to our functions. So what are the angles that we are plugging in? If you go to window, you will see the angles. Starts at 0 and goes to 2 pi. So notice when you press trace and you're at 0, it won't let you go to the left at all to negative angles because it didn't plug in negative angles to get the graph. Does that make sense? And why cannot go past 2 pi? Because the last value it plugged in was 2 pi. This is a very important thing. Theta step. It is saying I'm starting to plug in angle 0 into your equation, into your cosine equation. I'm stopping at 2 pi, and I'm using this as the increase when I plug it in. Now, what is this? This ends up being pi over 24. Okay? So let's think about it. How many pi's over 24 is in a pi over 4? How many times do I need to click over pi over 24 to get to pi over 4? 6, right? Okay, good. Well, go into your graph and go to trace. And remember, at the pi over 4s for this cosine graph, we were at 0, the origin, right? So 1, 2, 3, 4, 5, 6. Where are we? Well, we're essentially at 0. Your calculator does not give you R because it automatically converts it to X's and Y's to graph this, and we'll talk about that conversion in a second. Okay, some values to keep in mind: 3.1415926.535 pi. Pi will eventually get hit when we get to 24 clicks. 24 pi's over 24. Boom. Then we will keep going till 2 pi. Fantastic. Okay. Now watch what happens if I change this theta step to like pi over 2. My graph changes to that. What? Why? What's going on there? Does that mean this is wrong? No, just used 0, pi over 2, pi, 3 pi over 2, and 2 pi, and plotted those points and connected them. Doesn't mean this is the correct graph. It just means they did not plot enough points. So keep it at pi over 24. And that's nice. All right, do me a favor. Go ahead and graph cosine of 3 theta. Cosine of 3 theta looks like this. Now, I'd like you to do something for me. In your calculator, go back into y equals. We have it changed to 3 theta. Change this line to a line with a circle after it, a dashed circle. And go ahead and press graph again and look at it. Observe something that I want you to observe. Go ahead and graph cosine of 2 theta again and look at what happens. So here's the graph of cosine 2 theta. You can see how it's created using increasing angles. But if we look at the graph of 4 cosine 3 theta, what's different? It traces it twice. What does that mean?
What did you do again?
So you go y equals, you go to the left, you press enter until you get this line in a circle. What does this mean? What does that mean that it went over it twice? Right. The increasing angles yielded the same result. And it didn't go over it twice for cosine of 2 theta, right? Just went over it once. Well, why is that? Because the entire graph, all of these points, are created between 0 and pi, not 0 and 2 pi. So your calculator is going from 0 to 2 pi, but it ended up tracing it over it again because this graph, unlike the graph of the cosine of 2 theta, this graph is created from 0 to pi. Whereas your red graph of cosine of 2 theta was created from 0 to 2 pi. And then after you go past 2 pi, it would be traced over. Now, watch that. I'll do it really quick. Let's go back to the cosine of 2 theta. I'm going to adjust my window to 4 pi. Now, if I adjust my window to 4 pi, we should see it go over it again. So here is 0 to pi, and then we are going over it again because I've increased my thetas that the calculator is plugging in to be between 2 pi and 4 pi. Okay, so great. So keep that in mind. Now, let's see if theoretically we can, well, also let's graph another one. Let's graph the sine of 2 theta. You know, do 4 sine 2 theta. Extremely similar to cosine 2 theta, right? But shifted. Why? Mr. Johnson, idea? Because sine values are different than cos values. Yes. Like the, exactly, like the cosine and sine graphs are shifted. These are shifted, right? Well, give me like an easy way to understand why the petals of cosine are on my axes, whereas the petals of sine are not. Because cosine of 0 is
1.
but the sine of 0 is. So watch when I press trace. I'm not going to start at this point 0, 4. I start at essentially 0, 0, but you think of it not as 0, 0. You think of it as an angle 0, giving you a radius of 0. And then as you increase the angle, here's my positive radiuses. When I end up here, it looks like I'm the furthest away. So that must be when sine is at its maximum value. What is the maximum value that sine can have? 1. And what value do I plug in for theta so that this is the sine of something that gives me 1? Sine of what is 1? Yes, pi over 4 is the angle I plug in because the sine of pi over 2 is 1. Watch this. Go in and plug in pi over 4 for your theta. Once you press trace, you can do this, and boom, that's where you are. Okay, because the sine of pi over 2 is 1. So that's why we go all the way out there. Okay, so cool. Now, can you graph these without using your calculator? The first two, you should be able to get. See if you can get the last one. Then go ahead and graph the last one using your calculator if you give up. Okay. All right, well, Mr. Williams, what do you think r equals 3 looks like?
Circle.
Circle, radius 3. No matter what theta is, my r is 3. Excellent. What do we think about theta equals pi over 6? Straight line with theta always being pi over 6. Excellent. Positives and negatives. Okay, we think about r and theta being the same, like y equals x. Okay, so 0 for theta means 0. Good. As I increase my angle, my r increases. Graph y equals after you thought about that and see what the graph of r equals theta is. Make sure it's the same as what you thought. Also, if you guys took a book out for me, return the book to the shelf. I have your names. I will find you. We end up with a graph that looks like this. That's what my calculator says. Oops. Cool. But it would be even cooler if I did something. But my calculator says it looks like that. My calculator is not doing this graph justice. Why? Because theta stops at 2 pi. Increase your window. Zoom out. This graph should not stop. This graph does not repeat. Right? That's lame. But let's go to 18 pi. Yeah, but it really actually doesn't do it enough justice. Why? Has to do with this. Why does it not do it enough justice? No. Yeah. What could I start at? What if we plugged in negatives? Would that be the same? No. Watch what happens. Now we start outside in because it's plugging in the negative values, so it's like the huge negative values. And then we're going to get to 0. And now we go positive. They end up being reflections of each other. So this graph, if you think about negative angle, so negative, pi over 6, it'd end up, let me do a little bit better. End up going like that, and they would intersect each other a lot of times down here and up there. And that's what the graph of r equals theta looks like, if you think about it. Now, when I said it was cool, but it could have been cooler, it's because, let's go and start at 0 to 18 pi of theta, sine theta. Watch how my leaves are just going to get bigger and bigger and bigger. It's going to be cool. right? This is fabulous.
Are any of the leaves the same size, or are they all like increased?
So like the biggest leaves are the same. Are yes, each leaf is bigger than the previous one, right? Because you keep adding your angle, so none of them are the same size. That's awesome. All right. We can change these polar coordinates into XY coordinates, though, which we want to do sometimes if we want to. It's a good entryway into the calculus of these polar equations. Now, I'm just going to get through it. We kind of investigated a little bit more than other classes. I will tell you that we will use our friend, Mr. SOHCAHTOA, and trigonometry to find the XY coordinates of any point in the polar world. So recall SOHCAHTOA. This point comes from an angle. We'll put 3 pi over 4 there, but we understand that the 3 pi over 4 is here, but just because I will create a right triangle. The distance would be the hypotenuse, right? So we got 2 parts of a right triangle. That's all we need, the angle and one of the side lengths to find the other side lengths. In previous classes, when we had more time, I had them just figure this out, and some of them did. So to find this y, what part of SOHCAHTOA would I use if I have the angle and the hypotenuse? What part of SOHCAHTOA, when I have an angle and I want to find this side length and I have the hypotenuse, would I use? The SO part. Sine of 3 pi over 4 would equal y over 2, which is why y is 2 times the sine of 3 pi over 4. Sine of 3 pi over 4 is positive root 2 over 2. 2 times positive root 2 over 2 is root 2. That's great. Now, for the x part, what would I use? The ka part. Cosine of 3 pi over 4 is equal to x over 2. X is equal to 2 cos 3 pi over 2, 3 pi over 4. Cosine 3 pi over 4 is negative root 2 over 2, times 2 is negative root 2. So I've just turned this into an xy. And that's good, but it's this idea of the sine of my angle times my radius gives me my y-coordinate. The cosine of my angle times my radius gives me my x-coordinate. It's that idea that we are going to use a lot because we now have the capability of turning these into x equations and y equations if we wanted to. We'll call this polar to Cartesian. An x-coordinate is always going to be the radius times the cosine of theta. The y-coordinate will always be the radius times the sine of theta. And that actually enables me to create some equations. If I want to convert things into x equals equations and y equals equations, I can do so. If I'm told that r is 3 cosine 2 theta, well, we know r is all of this. I can plug that into that equation and say, oh, well, just x is 3 cosine 2 theta times the cosine of theta, r cosine theta. All my y's are r times the sine of theta, 3 cosine 2 theta sine theta. This helps me if I want to find the slope of a tangent of a polar graph. Now we are in calculus territory. Because the problem with derivatives of r is they give you r prime negative 4 sine theta But this r prime is not going to give me a slope of a tangent. In fact, it's actually dr d theta is r prime if I took the derivative of r. That's not dy dx. Slopes of tangents are dy dx. So what do I have to do to get a slope of a tangent? Well, I'm going to have to use y equals r sine theta, and I'm going to use y equals r cosine theta. And if I take the derivatives of these with respect to theta, thank you. And if I take the derivatives of these with respect to theta, I would get dy d theta and dx d theta. What can I do to those two, Miss Ali, to get dy dx? That's exactly right. If I divide dy d theta by dx d theta, I get dy dx because the d thetas would cancel. Now, in practice, it can be a little bit messy. Let me show you. We're going to find the slope of the tangent of 4 cosine theta when theta is pi over 4. Go ahead and graph 4 cosine theta in your calculator really quick. Because r sine theta is a product, and r cosine theta is a product. When I take the derivative of this and the derivative of this with respect to theta, I need to use the product rule. So dy d theta would equal the derivative of the first times the second plus the derivative of the second times the first. That's negative 4 sine theta times sine theta plus derivative of sine theta cosine theta times 4 cos theta. That's the derivative of y. I would divide that by dx d theta to get dy dx. Derivative of the first, negative 4 sine theta again, but now I have cos theta plus derivative of cos theta, negative sine theta times 4 cos theta. If I plugged in pi over 4 everywhere, I would find that I'd get 0 over negative 8, which is just 0. When I have a derivative, a slope of a tangent, that equals 0, what does that appear like on a graph? Maxes or mins, right? Or what type of tangent? Each word. Horizontal tangent. Now go to theta is pi over 4 on 4 cosine theta. Do you see a horizontal tangent? Man, don't want to take away this, but I have to. 4 cosine theta ends up just being a graph. Let's go to my standard zoom. Trace 6 clicks to get to pi over 4, right? 1, 2, 3, 4, 5, 6. There's pi over 4. There's a horizontal tangent. You can just, press trace and then plug in any value as well. Okay? Great. Also, that's for horizontal tangents. If you want a horizontal tangent, of course, we know that's when dy dx equals 0. Well, finding dy dx is pretty intense. I got to do dy d theta and dx d theta. But in reality, I don't have to be that intense about it. Why? If y equals 0, we don't have to worry about the bottom. I just need to worry about the top, the dy equaling 0. Well, in these polars, we just look at dy d theta. This will be very helpful for your quiz. For vertical tangents, we know that is when dy dx is undefined, right? What part of a fraction do we need to be 0 for something to be undefined? The denominator, right? So the dx part. Well, in the polar world, we'll just need dx d theta to be equal to 0. Make sure you have that written down. You'll have a question on your quiz like that. Okay, so that's how you find horizontal and vertical tangents. Finally, to find max and min r's, that's when we take our derivative and set it equal to 0. When I find r prime and set that equal to 0, I'll be able to find a max or a min. Now, give me a couple angles in which sine is equal to 0. When is sine 0? 0, pi, 2 pi, right? Now, what's very interesting about this, and if we looked at r prime, 0, pi, 2 pi. Now, understand r prime is negative, so between 0 and pi, let's think about pi over 4. Sine is positive there, but it'll be negative 4 times that positive value. So this would be negative, positive, negative, positive. We see we have a max at 0, a max at 2 pi. Well, looking at 4 cosine theta, oh, and we see we have a min at pi, right? Well, looking at 4 cosine theta at 0, what does it mean to be a max r? Well, this just means we're pretty far away from the origin. We are the max distance away from the origin. Okay, so 0 and 2 pi, we should be as far away as possible from the origin. This is the furthest we can be from the origin, 4 units away. But the min is at pi. Let's go back to pi. Oh my goodness, I'm at pi already. How can this min be at the same location as my max? Well, it's going to trace around at 1 more, yes, to get to 2 pi, but if we have a max r, that means I'm far away, right? If we had a min r, wouldn't that mean I'm like here? Very nice. Because r is negative at this location, but that's still a positive distance. Okay, so it's very, very important to understand. If you're trying to find a max r, sure, you're doing this. But most questions are going to ask you for a max distance from the origin. And though I haven't seen many questions try to trick us like that, we need to include the mins because min r's are still distances away. Okay, so when you're asked to find the max distance, also make sure to check the endpoints. I'm going to help you out on the next quiz. It's pretty hard, but it'll take us probably an hour of the hour and 30 minutes, and then the last lesson will be 30 minutes, but it's a fun lesson. I like this stuff. All right, thank you. You guys can go.